Hi, everyone. My name is Sabi Graywall. I'm going to be telling you about a recent paper called Improved Stabilizer Estimation via Bell Difference Sampling. This is joint work with Vishnu Iyer, William Kretschmer, and Daniel Liang. And the full version of the paper is available on the archive. So this work is about learning quantum states, and we look at three different learning models in this work. So let C be a subset of quantum states like product states or stabilizer states. And suppose we're given copies of an arbitrary quantum state psi. One learning model we look at is called the weak learning model, where we need to decide if psi is in our subset C or it's a Haar-random state. Promise one of these is the case. The next model is tolerant testing, where we need to decide if psi is epsilon 1 close to some state in our subset or it's epsilon 2 far from all states in our subset. And the notion of distance here can be fidelity or trace distance or some other distance measure. And the last model we look at is called agnostic tomography, where our goal is to output some state in our subset such that the fidelity between the state and our input state psi is within epsilon of the maximum overlap across all states in C. Yeah, there's a lot of notation here. I guess intuitively, the goal for agnostic tomography is to output the best approximation of psi in the set C. And we don't actually call this model agnostic tomography in this work, but in a follow-up work that's on the archive, we do call it agnostic tomography, and we explain the model in a bit more detail. So that's worth looking at too if you're interested. So in this work, we give weak learning, tolerant testing, and agnostic learning algorithms for near stabilizer quantum states. So for example, like one thing we do is we decide if an input state is near stabilizer or it's Haar-random, promise one of these is the case. And what I want to do next is just formalize what I mean by near stabilizer so I can state our results in more precisely. Okay, so to do that, we need to talk about the stabilizer formalism. Uh, so the first thing I want to mention is that Clifford circuits are comprised of Hadamard phase and CNOT gates. So any quantum circuit that's comprised of Hadamard phase and CNOT gates is called a Clifford circuit. And this is a very special subclass of quantum circuits. For one, they can exhibit quantum phenomena like superposition, phase, and entanglement. But on the other hand, they're not universal. Evolutions of Clifford circuits can be efficiently classically simulated. This is the Gottesman-Knell theorem. And the Clifford circuits form a subgroup of the unitary group, and this algebraic structure plays a large role in why the Clifford circuits find use throughout quantum information and like error correction, in producing T-designs, in learning algorithms, and so on. The outputs of Clifford circuits are called stabilizer states. So if I have a Clifford circuit and I apply it to the all zero state, I'll get a stabilizer state. And a key property to know about stabilizer states is that they're uniquely described by an abelian group of 2 to the n Pauli operators. And in particular, for each Pauli operator in the group, our stabilizer state will be a 1 eigenvector of that Pauli operator. And it's possible to show that this uniquely describes a quantum state. And in particular, we can now describe a stabilizer state with the generators of this group G. And since the order of the group is 2 to the n, we only need to list out n generators. So stabilizer states have like a succinct algebraic description. So like I mentioned, Clifford plus T circuits are not universal. Clifford circuits are not universal. But they're nearly universal. And actually, if we just add one single qubit gate, this T gate, we would get a universal gate set. And one should think about the T gate as a limited resource. In a lot of settings where the Clifford plus T gate set shows up, the problems become harder as more T gates enter the picture. And this is true in error correction, magic state distillation, near Clifford simulation, and even in like tomography algorithms. And this fact is true for any uh, single qubit non-Clifford gate. So it's not just the T gate, but a lot of the times we choose the T gate for simplicity. Okay, so now I can say the notions of near stabilizer that are relevant in this work. The first is the stabilizer fidelity. So the stabilizer fidelity of a state psi is the maximum fidelity between psi and all stabilizer states. So we maximize the fidelity between psi and every stabilizer state, and that's the stabilizer fidelity. And the other measure of near stabilizer is the non-Clifford count. So this is the number of non-Clifford gates that are necessary to prepare the state. So you get Clifford gates for free, and we're just counting the number of non-Clifford gates we need to prepare a state. Okay, so with that, we can state our results. So the first result I'll mention is our weak learner. So we show there's an efficient algorithm that decides whether a quantum state psi is preparable with at most n over 2 non-Clifford gates, or it's Har random promise that one of these is the case. And a corollary of this algorithm is that at least n non-Clifford gates are necessary to prepare pseudorandom states. And these are states that look Har random to a polytime observer. And this lower bound is tight under some reasonable assumptions that we explain in the paper. Our next result is the tolerant tester. So here we give an efficient algorithm that decides whether a state psi has stabilizer fidelity at least alpha 1 or at most alpha 2 for appropriate choices of alpha 1 and alpha 2. And the big caveat with this result is that it only works for certain constants, alpha 1 and alpha 2. So for example, like this blue region here shows the choices of alpha 1 and alpha 2 for which our algorithm actually works. So like for example, if we look at 0.2 and 0.85, it's like roughly in the blue region. So that's basically saying our algorithm can decide if there's a stabilizer state that's like within 0.85 fidelity of a stabilizer state, or it has at most 0.2 fidelity with all stabilizer states. But you can see that as soon as you get to like 0.79, our algorithm kind of breaks down. Like it's no longer like we can't really test past this region. So one interesting open problem is improving these parameters. Like for any reasonable choices of alpha 1 and alpha 2, it would be nice to have a tolerant testing algorithm. And then the last result I'll mention is this agnostic tomography result. So here we're given copies of a quantum state psi, and we're promised that the stabilizer fidelity of the state is at least cosine squared pi over 8. And we show there's an efficient algorithm that outputs a stabilizer state phi that witnesses this fidelity. So in particular, phi, the fidelity between our output phi and the input state will be with an epsilon of the optimal fidelity, with an epsilon of the stabilizer fidelity. And we have a more general version of this algorithm that works for any stabilizer fidelity tau, but it comes at a cost. The the algorithm solves the same task and uses like roughly linear number of copies, but it runs in time exponential in n. And it's worth noting that the naive algorithm uses exponential in n squared time. So for when tau is constant, our algorithm is a substantial improvement over the state of the art, or the prior state of the art, but it's still an open problem to see if we can do better. So it would be very nice to have an efficient algorithm for any constant tau. And we have no lower bounds for this problem either. So it's really a mystery of whether this is possible or not. Okay, so the workhorse in all of our learning algorithms is this quantum measurement called Bell difference sampling. And I want to say a little bit about how this works. So yeah, the first thing that we need to cover is this psi distribution. So let's say we have a string x of 2n bits, where the first n bits we're going to denote by a and the second n by b. We can define this operator wx as follows. Um, so on the first qubit, we have a poly x or a poly z, depending on whether the first bit of a and the first bit of b is a 0 or a 1. And this um, and it's this way for every single qubit. And so we can see that this wx is a poly operator. And in particular, we call it a Weil operator. It's the Weil operators are a subgroup of the poly group. And we can define this function psi of x as follows. We take a string x, and psi of x is then the squared expectation between psi and the Weil operator wx with this factor of 2 to the minus n. And it's not too hard to show that psi forms a probability distribution over Weil operators. Okay, now I want to explain what Bell sampling is. So here we have two copies of a quantum state psi. These cells are qubits of psi. And the way Bell sampling works is we pair off the first qubit of each copy and we measure in the Bell basis. We get 2 bits of outcome in the measurement outcome that we call x1 and xn plus 1. And we pair off each the second qubits in the same way, the third qubits, and so on. So we do this for all n qubits, and the final output is then the string x of all of our measurement outcomes concatenated together in this order. And we interpret the output of this measurement as a Weil operator. Okay, so what is Bell difference sampling? This is a quantum measurement introduced by Montanaro and then studied further by Gross, Nizami, and Walter. The first thing you do is you Bell sample twice to obtain 2 different strings, x and y. So this takes 4 copies in total. And then you output x plus y. And again, we interpret this output as a Weil operator. And what Gross, Nizami, and Walter showed is that Bell difference sampling it samples the Weil operator WA according to this distribution Q psi, which is the convolution of P psi with itself. And again, here's the definition of P psi that we saw a couple slides ago. So the rough intuition here is that we have a quantum measurement that consumes 4 copies of our state, and it will output a Weil operator, which is just a special kind of n-qubit poly operator. And the probability you see any particular one of these Weil operators roughly goes with the squared expectation value of the Weil operator with your state. And this isn't, this isn't correct because we have to deal with this convolution, but this is like a rough picture to have in mind. Okay, so I'm going to give a bird's eye view of how all of our algorithms work. It actually breaks down into just 2 steps. You Bell difference sample many times, and then there's some classical post-processing you do on the Bell difference samples. Like all of our algorithms follow the structure, and the crux of what we do is really in the analysis. So the name of the game is really finding structure in this Q psi distribution, the Bell difference sampling distribution, whenever you have some prior knowledge about psi, whether psi has large stabilizer fidelity, it's prepared with a certain number of non-Clifford gates, or if it's random, and so on. And so for the remainder of the talk, I'm going to sketch out how 2 of the algorithms work, just to give you an idea of what this slide really is trying to say. And so we'll start off with the weak learner. So this is, again, the algorithm that decides whether psi is preparable with like n/2 non-Clifford gates or it's random. So yeah, this is the goal of our algorithm, to distinguish between these 2 cases. And the first key lemma that we need to prove for this algorithm is that if psi is a random state, then every 2n minus 1 dimensional subspace of f2 to the 2n has q psi mass at most 2/3. So this is like an anti-concentration lemma for the Q psi distribution when psi is Haar random. And the conclusion that we can draw from this lemma is that if we Bell difference sample a Haar random state like a linear number of times, then the samples that we see will span all of f2 to the 2n. Okay, so yeah, so here's our conclusion. Our samples will span all of f2 to the 2n. And on the other hand, we're also able to prove that if psi is prepared with n minus 2 over 2 non-Clifford gates, then Q psi is actually supported on a 2n minus 1 dimensional subspace of f2 to the 2n. Meaning if we Bell difference sample a state psi like this, the span of the dimension of the span of the samples will never exceed 2n minus 1. And this suggests the algorithm, right? So our weak learner is then we Bell difference sample like a handful of times, and we compute the dimension of the span of the samples. And if that dimension is 2n, if it spans all the entire space, we'll output Haar random. Otherwise, we'll output, n minus 2 over 2 non-Clifford gates. Cool. Okay. So here's this. So we're going to move on to the agnostic tomography algorithm. The goal here is, so we know there's a stabilizer state phi such that the fidelity between phi and our input state is at least cosine squared pi over 8. And we want to find that stabilizer state phi given copies of psi. In order to explain this algorithm, I have to introduce some notation. So let Weil psi be the abelian group of Weil operators, such that the Weil operators stabilize psi up to a sign. So psi is like a plus minus one eigenvector of the Weil operator. And we call this the unsigned stabilizer group. So for most states, this will actually just be the identity operator. But we can make a couple of observations here. So let's say that Weil psi, the order of Weil psi is 2 to the n. And that can only happen when psi is a stabilizer state. And there are 2 to the n stabilizer states that have the same unsigned stabilizer group. So like an example to make this clear is if we take any computational basis state, we have Weil ket x is the poly z's. In order to specify a particular computational basis state, you need to assign plus minus one phases to the poly z's. And since there are n generators of this group, you have like 2 to the n choices of where to put minus one phase and not. And so the main takeaway of this slide is that if you have an unsigned stabilizer group of order 2 to the n, you are specifying an orthonormal basis of stabilizer states. Okay, cool. So let's see. So the first key lemma required to give an algorithm for this task is the following. So suppose we have a state psi whose stabilizer fidelity is at least tau, and let phi be the stabilizer state that witnesses this fidelity. So the fidelity between phi and psi is tau. Then Bell difference sampling psi n over tau to the 4 times suffices to guarantee that we've sampled a complete set of generators for Weil phi. So we sample a bunch of times, and there's a subset of exactly n Weil operators in our sample that generate Weil phi. And this lemma is again just we use the fact that psi is close to some stabilizer state to prove some structure on the Q psi distribution. And so taking stock of what we have, we're able to sample many times, and we know inside of the sample there is a set of generators for Weil phi. We still need to find the subset of n samples that generate Weil phi, and then we need to assign plus minus one phases to specify a specific stabilizer state. So again, like we saw in the last slide, Weil phi is specifying a basis of stabilizer states, and we need to add ±1 phases to the generators to specify a specific state in that basis. So that's what remains in order to accomplish our goal. Okay. So the last lemma that we need for this is the following. We have vial operators, if we have vial operators Wx and Wy, where Wx is in the unsigned stabilizer group of phi, and Wy is not in this unsigned stabilizer group of phi, then we can show that the squared expectation of Wx is at least 1/2, whereas the squared expectation of Wy with psi is at most 1/2. And of course, this lemma, suggests a way of filtering out which vial operators are in the unsigned stabilizer group and which ones aren't. And so with that, we can actually state our algorithm that accomplishes our learning goal. So the first thing we do is we take like order n Bell difference samples. So we saw a lemma on the last slide that guarantees that this will sample with high probability a set of generators of vial phi. And then for each sample xi, we'll estimate the squared expectation and we'll discard the sample if the squared expectation is at most 1/2. So the lemma that's still on the slide here tells us that we're throwing away the vial operators that are not in the unsigned stabilizer group. Okay, so at this point, we can check if the remaining samples, whether or not they generate an unsigned stabilizer group. So if the remaining samples don't generate an unsigned stabilizer group of order 2 to the n, if we discarded too many samples, then our algorithm will just reject. Otherwise, we do have an unsigned stabilizer group of order 2 to the n. Again, this is specifying an orthonormal basis of stabilizer states. And we'll call this unsigned stabilizer group S. So in the last step, we'll just take fresh copies of psi and measure it in this basis specified by S, and we'll output the state that appears most often. So again, so S is an unsigned stabilizer group, and we know with specifying 2 to the n stabilizer states, one of which we know is ket phi. And so this last step is just using the fact that we're promised that psi is closest to ket phi. So in particular, at least a cosine squared pi over 8 fraction of our measurement outcomes will correspond to the state ket phi. And I also want to mention that the output here is polynomially sized because our output is a stabilizer state. So in particular, we can do step 4 and output like the list of generators for the stabilizer state phi. Okay, to wrap up, I just want to mention that I didn't sketch our tolerant tester or the exponential time agnostic tomography algorithm. But if you understand the two algorithms I did sketch out, it'll make it, they have a very similar flavor. So yeah, and okay. I want to conclude with some open problems. The first thing is giving an efficient agnostic tomography algorithm for stabilizer states beyond this cosine squared pi over 8 limit, or prove that this is where the limit is. Give a tolerant tester with better regimes. So again, ours only works for very particular constants. So improving that would be interesting. And perhaps the most ambitious open problem remaining is just giving an algorithm to estimate stabilizer fidelity. So you're given copies of a state and you want to give like an additive, some estimate of the stabilizer fidelity to some like additive accuracy. Cool. Okay, that's all I had. Thanks for listening. If you have any questions, feel free to email me or any of my co-authors. Thanks.